session. Right. Okay. Let's start over. So basically, the first I will show you the big picture of the cryptographic algorithm. So they could divide it into two groups, what we call it as a classical and the modern. In the classical cryptographic algorithms, that is the historical ones, we usually divide into two groups, what we call it as a substitution ciphers and the transposition ciphers. Substitution ciphers, we have two groups again. We call it as monoalphabetic substitution and the polyalphabetic substitution. Some of the algorithms which we discuss, like Caesar cipher, comes under monoalphabetic substitution. That means we substitute one character at a time. And the polyalphabetic substitution will substitute more than one character at a time. So all of them are substitution ciphers. We substitute the letter with another letter according to some algorithm. As I described in the last week, since all the languages in the world having some letter frequencies, so those substitution algorithms may not be able to use anymore. They are kind of obsolete. Then there are a category, what we call it as transposition ciphers. In these transposition ciphers, basically use entire block. So we call them as a block ciphers as well. So those we handle data blocks at a time. So those are all classical or historical algorithms which we briefly discussed in the last week. Today we focus on the modern cryptographic algorithms and we discuss how do we going to use them. So these modern cryptographic algorithms, basically we divide into two groups. Again, we call them as symmetric key cryptographic algorithms and the symmetric key cryptographic algorithms. Symmetric algorithms, we use a single key for encryption as well as the decryption. So some of the symmetric key algorithm, encryption algorithm and the decryption algorithm, both are same algorithm. That means same implementation can be used for encryption as well as decryption. But some of them, we have two different algorithms, but we use the same key. The symmetric key prefers because of the key. So we use the same key for encryption as well as decryption. If so, those algorithms call it as a symmetric key algorithms. So when you take these symmetric key algorithms, those symmetric key algorithms we can divide into again two, which we call them as a block ciphers and the stream ciphers. Block ciphers, we work as data blocks. That means more than one character at a time. Stream ciphers, we use one character, only one character at a time for the encryption and decryption. Most of the modern encryption stream ciphers, basically we are not really using like RC4 seal type of algorithm. Instead of what we do, we convert this block cipher into the stream. So I will explain you later on in this lecture how we do that. So when you come into the block cipher category, we could see several block ciphers used in the industry. Among them, international standard right now, call it as the AES, Advanced Encryption Standard. We will roughly go through this advanced AES algorithm and see whether how it works. And then we have the previous standard for the encryption, call it as a DES, Data Encryption Standard. So there is an enhanced version of the DES, we call it as a triple DES. In roughly, we will learn the DES, triple DES, and AES in this class today in the morning session. So then, in the modern ciphers, then there is a category called public key cryptography. We call them as asymmetric key cryptographic algorithm as well. So the asymmetric key cryptography, we use two different keys, one key for encryption and the other key for decryption. So under the asymmetric key cryptographic category, we could see several of them, asymmetric key cryptographic algorithms. We call them as RSA, DSA, Diffie-Hellman. One is missing in this diagram, that is elliptic curve cryptography. So there are kind of among these algorithms, so RSA is heavily used, and with the devices like mobile phones, we recommend to use elliptic curve. And the Diffie-Hellman public key cryptography algorithm mainly used for the key exchange purposes. I will let you know this within today. So the focus today is to study RSA, Diffie-Hellman, elliptic curve, AES, DES, triple DES, and usage. How do you going to use them? I'm not so going into the deep of the mathematical part of that because it was already covered under the other course. So I focus on application part of it. Right. In brief, as you already know, the symmetric key encryption, we use the same key for encryption as well as the decryption. We have a plain text which human readable. We apply them to the encryption algorithm and apply a security key that converted into the ciphertext. So in the encrypted form. So those ciphertext we can feed it into the decryption algorithm and apply the same security key so that it can we can get back the plain text. So that's how a symmetric key cryptography algorithm works. The algorithms are symmetric on the point of key. So some of the algorithms are symmetric on the point of algorithm as well, but we categorize those as symmetric key by looking at the key. Keys are symmetric. Symmetric means the same key used for encryption as well as the decryption. Right. So those symmetric key cryptography algorithm has several issues. The major issue we are having with this symmetric key cryptography is a key distribution issue. That means if you use those algorithms for encryption of the data in between the senders and the recipients of the network, where we can generate a key, encrypt that data, and send to the recipient. So in order to decrypt that at the recipient side, recipient need the key. How do you going to send that key to the recipient? That is the issue of the symmetric key cryptography. Because when you send the key through the network, attackers can get the encrypted data as well as the key, and then they can decrypt it. So there are different set of algorithms we are having, call it as a key distribution algorithm. We have to use those specific key distribution algorithm to distribute those keys. Otherwise, symmetric key itself has an issue of the key distribution. Symmetric key alone cannot be practically used in day-to-day activities because we cannot send that key from the sender to the recipient through the same medium. So that's the major issue. Then we have an issue of scalability. That means if you want to kind of having a sacred communication in between groups, how many keys we need. So for example, if there are two people, we can have a one key shared between. If we have three people, we can have three keys, but we have four people, we need to have six keys like that. So if the number of groups, number of nodes increasing, the keys we need exponentially increase. So that issue, we call them as the scalability issue. So these symmetric key algorithms are not scalable when we deploy those or when we try to implement it in the large scale. So there are solutions for that we discuss as well in the later on. This is the second issue. In the third issue, basically any cryptographic algorithm having that issue, that is usually, as you know, brute force attacks. So since those key sizes are fixed size, so if someone can search all possible combination of those keys within some kind of real time, so obviously they can break or they can decrypt the data. So if let's say we have 128-bit longer key, then maximum number of keys we can have in this algorithm is 2 to the power 128. So having 2 to the power 128-bit keys is enough to resist the brute force. It depends on the power of compute. So if you have more powerful computers, so they can search all possible keys in a short period of time. So we need to have a larger keys. So in the symmetric key algorithm, obviously vulnerable for the brute force. So in order to be resist to the brute force attack, we need to have algorithm with larger key sizes. Right now, recommended key size of a symmetric key cryptography algorithm is 256-bit keys. I'll come to that in a minute. So in as a conclusion here, I I will repeat. So those symmetric cryptographic algorithm has three issues. It is vulnerable for brute force. It has a scalability issue. There is a key distribution issue. So, however, when you look at the strength of those symmetric key algorithm, they are very fast and efficient comparing to the asymmetric key. So when you have a bulk data to be encrypted, like your hard disk or some database records, so obviously we have to use symmetric key cryptographic algorithm. So if you try to use asymmetric key cryptography to encrypt, decrypt the bulk data, we have to wait for years. So as you know, perhaps already, like RSA algorithm, they use heavy mathematics, power calculations. So those power calculations need so many computing power as well as processing power. So if you want to encrypt megabytes of data using such algorithms, obviously we need to be wait for months or the years. So, however, in the symmetric key, we could do it faster. So, only thing is we need to have a solution for the scalability and key distribution issues. So the solution for those two issues are the asymmetric key cryptography. The second lecture today, I will show you how can we use asymmetric key cryptographic algorithm to sort it out the issues in the symmetric system. Later on, I will show you that. Right. So, as you may already know, so in the symmetric key cryptographic algorithm, we use the same key for encryption and decryption. Usually, we use letter E to represent encryption. So, K represent for security key K. So, EK means encrypt data with key K. X is our data. So when you apply function EK to the data X, we get back the ciphertext Y. So then usually we use letter D to represent decryption, K again the key. So DK means decryption with the letter K, decryption with the key K. So when you apply the ciphertext Y to the decryption algorithm, that means DK, we will get back the plain text X. So that's how this symmetric key cryptography works. So in the beginning of this computer science, we are using different symmetric key cryptographic algorithms. But later on, when the internet working started, people realized we need to use a common algorithm for encryption and the decryption. So people try to create a standard for that. So the US started creating these standards, and they have called some competition in between the existing cryptographic algorithm in the world at that time, and they have selected one algorithm uh, proposed by the IBM. Original name of this algorithm is Lucifer. IBM was a big company at that day, so that algorithm was kind of renamed as a international standard for data encryption. It was shorter name for that is called DES, Data Encryption Standard. If you want to get the detail of that, it's a public algorithm. You can get the detail. If you want to get the detail of that, search for FIPS publication 46. FIPS represent Federal Information Processing Standards. Federal Information Processing Standard publication number 46 describes the REST algorithm structure. If you interest that, you can get that and read that. By the way, so I am having heavy rain outside. Can you still hear me clearly, or you see the
Yes,
get?
sir.
Sorry,
We can hear you.
can you can you hear me clearly?
Yes, sir. Yes.
Ah, great. Because there is raining, heavy raining outside, but I don't. I want to make sure you are hearing me. Okay, right. So we will continue. Right. So in the DES algorithm has a in principle DES algorithm has 56-bit keys. That means a 7 byte. 7 byte. It's similar to the 7 byte password. So you already did the activity. So there you realize brute forcing the 7 byte password may take just few days or the seconds in some instance. So because of that, if you have any cryptographic algorithm which uses a 56-bit keys, that means 7 byte, is not strong enough. So kind of few years ago, it took, in 2010, it took some hours or the days. Now it's just minutes to brute force 256-bit keys. That is how many keys we have maximum there, 2 to the power 56 keys. Because of that, we cannot use this algorithm for our activities today. So we need to have alterations for that. One of the alterations, or one of the uh, enhancements we do for the DES algorithm, call it as a triple DES. In simple, in the triple DES algorithm, what we do, we encrypt our data more than once in several rounds. So for example, we have a plain text as shown in this diagram. We have a plain text, clear text. We encrypt that using the test algorithm using a security key called K1. And when it produces the ciphertext, we feed back this ciphertext again to this encryption algorithm and apply a second key called K2. And we repeat that for the third round with a third key called K3. So, for example, what we do, we have a ciphertext encrypted in 3 rounds with three different keys. So then, if someone wants to break that, brute force that scenario, they have to brute force all these 3 keys. That means the total key length, each key is 56 bit, total key length is 167, no? 160, 168 bits, 168 bit longer keys we have to brute force. That means we have the 2 to the power 128 bit number of 168 bit keys, 168 bit to the power 168 bit possible combinations. So brute force in that still kind of difficult. So if you do that, encryption. So how do you do the decryption? As you may understand, we need to apply the keys opposite opposite direction to having the decryption. So when we get the ciphertext, first we need to apply key K3, and then we need to apply key K2, and then we need to apply K1. So that will decrypt each rounds, and finally we will get back the plain text. So this is the way we make those encryption much stronger, much stronger. However, when you do some encryption and it kind of shuffle the data throughout the block in a way, no one will be able to identify the data or patterns in there. So, so usually when you encrypt the encrypted data, we may not really improve in the strength. In other words, when you encrypt the data again and again and again, that doesn't mean so we are kind of strongly doing the shuffling. So in other words, when you encrypt the data again and again and again in several rounds, so perhaps we will weaken the encryption strength, because when you shuffle the data, shuffle the data, shuffle the data again and again, perhaps we will come back to the original plain text, closer to the plain text, right? So because of that, the cryptographers are not advised to encrypt the data more than one round. But since we want to kind of resist to the brute force attack, we have designed this triple days algorithm and apply the three different keys. But security cryptographic researchers clearly showed that having three rounds of operation may not strengthen the encryption, it will kind of weaken the encryption. So because of that, usually we are not recommending to do that in three different rounds. So we only recommend to do that only in two different rounds. But we are having this third round to do a backward compatibility. I will let you know in the backward compatibility in the minute. Right. So, some people will apply the triple days with two different keys. Because of those reasons, some people are not using three different keys. Instead of, they might use two different keys in triple days. So if they use two different keys, how do they do it? Like here. So they do. How do they do is, they use the K1 in the first round, then they use the K2 second key in the second round, and they will again use K1 in the third round. That means we use two keys, but in order K1, K2, and K1 back. So in that way, we could apply the triple A as well, but we have to make sure we are not using same key in two consecutive rounds. Why so? If you do it, we will kind of reduce the triple days into the single days. How? So for example, let's say we have the clear text here, plain text. We apply for the encryption algorithm and apply the K1, security key K1. It will encrypt the data. So then we feed that encrypted data to the same algorithm and apply the same key that not really do the encryption, that will decrypt the data. Because triple days is a fully symmetric algorithm. It uses the same algorithm as well as the same key for encryption as well as decryption. So in the first, we apply K1 to the data, it will encrypt. And when you feed that data and apply K1 again, that will decrypt. So that means the first two rounds get neutral each other. So then encryption only happens in the third round with K2. So in other words, if you apply the same key in two consecutive rounds, like here K1 and K1, triple days will get downgrade into the single days. So honestly speaking, so we are having these three rounds here to make that feature, because sometimes we may have a single days implementation and one end, the other end we may have a triple days implementation. So then the if these two parties want to talk to each other, the triple days implementation need to be downgraded to single days. Otherwise, it may not going to work. So any triple days implementation can be downgraded to a single days by giving same key in two different consecutive rounds. Otherwise, we cannot do the communication. So as you see, so we can do downgrades, or we can have a backward compatibility by giving the same key in two consecutive rounds. So if I go back here how we do it in triple days. So we have to use three different keys to get their full strength, or else we can have two keys, two keys like here. There we need to use K1, K2, and K1. We should not use K1 and K1. So if you use K1 and K1 like that, so then it is equal to the single days. So that's how we basically use a triple days algorithm nowadays. Triple days algorithm we use with two keys or three keys. So if you use it with two keys, we have to be careful. So the keys which use in the consecutive rounds should not be equal. So that is the condition. All right. So with doing all of those things, we can increase the strength for the key maximum to the 56 multiplied 3. That means 128 bit. So that is the maximum key size we can get, 128 bit. So we are not advised to use the encryption more than 3 rounds, because then it may eventually get decrypted. So otherwise you might argue that we, instead of 3 rounds, can't we use 5 rounds? Can't we use 10 rounds to do that? So we can't do that, because that is may not, it's badly affect the strength of the data, encrypted data. So we only do 3 rounds. So there we can get maximum of 168 bit keys. So that is the maximum we can do with the desk. So as you know, the power of computers are increasing day by day. 168-bit keys even not so strong to resist the brute force in the present context. So we need to have the larger key size. So with the triple days, we can't do that. We need to have alternatives. So then somewhere around 2000, the US government again conduct a competition to find it out a better algorithm, better alternative to the triple days. So the algorithm they found was called it as AES, Advanced Encryption Standard. Actually, they had a competition again, and they selected 15 candidates, uh, and among they selected 5 in somewhere 1999 for the final competition. So among those 5, they selected the algorithm called it as Regindal. Regindal, submitted by few Belgian cryptographers as the winning algorithm. Later on, they have renamed that to AES, Advanced Encryption Standard. AES refers to Advanced Encryption Standard. Again, that AES is an open standard. You can get the specification by searching FIPS publication 197. Federal Information Processing publication 197 fully explain the advanced encryption standard. So if you want to get the detail, you search that and read the document. I will do the highlights. I will teach you the highlights. So what would be the requirements of designing the AES algorithm? So basically, we need to have an algorithm with larger key sizes. So those AES algorithm designed in a way to have 3 different key sizes. This algorithm can work with 128-bit keys, or 192-bit keys, or 256-bit keys. At the initial stage, like around 2000, we were using this algorithm with 128-bit keys. Now, we are on the last phase of this AES algorithm. There, we recommend to use 256-bit keys. So for example, the lifetime of those algorithms, if I discuss, this algorithm introduced to the world in 70s. There were this competition conducted in 1977, and somehow DES was announced to the world at the end of the 1970s. So we were using the DES algorithm until some 2002, 2005 periods. So after that, we are really now using DES. So for example, DES algorithm was using roughly 30 years. So because of that, usually we tells lifetime of the symmetric key algorithm, maximum lifetime is 30 years. Similar to that, we announced the advanced encryption standard in 2000. So we expect this algorithm would expire in 2030 because by 2030, so we get 2030 means after another 7 years time, not so far, just after 7 years, we believe the machines we are having will easily brute force 256-bit keys. So at the time, this A is going to be expired as well. So, so we have 7 years more to use AES. So in next 7 years, we need to find some alternative to the advanced encryption standard. Still, people are looking for good alternative algorithms for AES. Until we find the one, we have to use AES, Advanced Encryption Standard. So size of the key we can use maximum is 256 bit. That means we can have 2 to the power 256 bit keys maximum in AES. Right. So I forgot to mention the DES algorithm as well as the AES algorithms. Both are block ciphers, block symmetric algorithms. Block ciphers means they use the same algorithm. They use a more than one character at a time. That is what we mean block cipher. So in the stream cipher, we use one character at a time or one bit at a time. But the block, we have to use a data block, more than one character at a time for the encryption and decryption. In the DES algorithm, we are having 64-bit blocks. That means in one encryption, a single encryption, we need to have 8 characters. 8 characters. If you have a one character, we cannot encrypt with this. We need to have 8 characters to encrypt with the DES. So that in practically we may have 2-3 characters to be encrypted. Then how can we do that encryption? We will discuss in a minute how to do that. So for that, we are using a technique called padding. I will discuss in a minute. Usually, modern ciphers, all the modern ciphers are block ciphers. DES have the block size of 64 bits. That means we need to have 8 characters at a time for the encryption. So when it comes to the AES, Advanced Encryption Standard, our block sizes are much larger. Our block size is 128 bits, 16 characters. We need to have 16 characters at a time for the encryption. 16 characters at a time. Otherwise, we cannot encrypt. That means we need to feed some data to make it 16 ready for the encryption. How do we do that? We'll discuss. Right. So AES is a block cipher which use 128-bit blocks and uses 3 different key sizes. Okay, if I discuss a little bit of algorithms, cryptographic algorithms which were in the last round of this competition. So there were several of them, like 5 of them, call it as Mars, RC6, Rachindal, Sprit, Two-Fish. Two-Fish algorithm still we use in the industry uses Two-Fish. So the Rachindal is the standard algorithm, advanced encryption standard, Rachindal. So when you compare the efficiency of those algorithms, Rachindal encryption cycle is kind of slower than Two-Fish. So as you see, it's here, it says very fast, very high in the two fish, marginal in the regenda, kind of regenda. However, we pick that as the next standard. There should be a reason for that, no? Reason is, so the Regendal has the fastest decryption algorithm. By the way, Regendal uses different algorithms. One algorithm for encryption, the other one for decryption. This is not so like. So this use the same algorithm for encryption as well as the decryption with the same key. The Regendal uses the same key, but their encryption algorithm and the decryption algorithm is different. So their encryption algorithm is slow, decryption algorithm is faster. So, so that is the exact reason we use Regendal or AES as the next international standard. Why? So when you consider the encryption and the decryption happens in the world, assume you are encrypting your hard disk. So you may assume that you may imagine that. So when you encrypt your hard disk, you might do it only once. But every time when you access this information, you have to decrypt it. So take an example, you are storing some data in a database in the encrypted form. So you are encrypting that data and store that data in the database once. So every time you are retrieving that data, you have to decrypt. So that means the decryption cycle in the world is really larger comparing to the encryption cycles. Someone can wait some time to happen the decryption, but people would like to use faster. Someone can wait till the data get encrypted, but they would like to use that data faster. That means we need faster decryption algorithm. Regendal has the fastest decryption algorithm comparatively to others. So that's why it was selected and we are using that as an international standard right now. International Standard for Data Encryption, AES, Advanced Encryption Standard. You can see the detail, as I said, in the Federal Information Processing Standard 197. So summarize the features, three main features we want to focus. First one is the block size. Size is 128-bit, 16 bytes. Then the key size. There are three different key sizes, 128, 192-bit, and 256-bit. We recommend to use 256-bit keys. Internally, Regendal use 10 rounds of internal processing with 10 individual keys derived from the master keys. So usually when you want to get a feeling in the abstract level how this encryption decryption happens, so let's have a look in little detail how we implemented advanced encryption standard, how we implement their encryption side. Encryption side. There is a heavy mathematics behind the algorithm. I am not going to mathematics as I said at the beginning. So I will just show you the method we implemented the AES encryption. For that, we are using a matrix multiplication. Matrix multiplication. So whatever the data we want to be encrypted, we organize them into 4 by 4 matrix. 4 by 4 byte array. So that means 4 multiplied 4, 16 bytes. So the block size is 128 bits. So we must have 16 bytes organized into the 4 by 4 matrix to start the encryption cycle in AES. Right. After that, what we do in the first thing, we basically, each byte of, in the array, we will map into the new byte based on the key. So after that, we get some new set of 16 bytes. So then those 16 bytes we will rotate in some pattern. How do you do that? We keep the first row as it is. We rotate the second row by 1 byte, the third row by 2 bytes, and the final row by 3 bytes. So then it will produce the new 4 by 4 matrix. Then again, we do some kind of expansion of the data in each byte of this data according to the key and map that into a new byte array. So those mapping process happens based on the keys always. And for that, we are having a pre-calculated tables, what we call them as X boxes. X boxes. So in the encryption and decryption, we are not doing those calculation. Instead of, we have a pre-calculated tables, call it as X boxes. At the encryption, we just do lookups, table lookups, like we are looking in the log values while we want to multiply numbers. We have log tables. We just look at the log values and then get the inverse and then get back the number like that. So we have pre-calculated tables in those encryption implementations. We call it as X boxes. Based on the key, we are looking for the X boxes cell and replace uh, bytes on the plain text with the table characters. So that's how we basically do. Our encryption is some kind of combination of replacing the data with X boxes and rotating or mixing the data according to some patterns. So this is just to give you a feeling about how to implement that. All right. So at that point, I have discussed the two major algorithms which we're using today for encryption and decryption of the data. So both of them which we discussed are symmetric cryptographic algorithm. So DES and the AES. The DES algorithm was obsolete. We cannot use that. Instead of, we have to use enhanced version of DES that called as a triple DES, or else we have to use AES, Advanced Encryption Standard, with 256-bit keys. So both of them are block ciphers. DES uses 64 bits at a time for the encryption. AES uses 128 bits at a time for the encryption. So since those both algorithms needed data block to be encrypted, so our plain text should be equal to the block size or equal to the multiplication of the block size. So, but practically when you do encryption and decryption, we may not have that. So for example, in the DES, perhaps we want to encrypt the 9 bytes. DES uses 8-byte block. So we can use first 8 byte and encrypt with the DES, and then there is a 1 byte left. How do you encrypt that byte? Because 1 byte cannot encrypt with the DES. Similar in the AES. In the AES, if you have 9 bytes, we cannot encrypt because AES needs the 16 byte. So we need to make that 9 byte to be 16 and then feed it to the encryption algorithm. How do you do that? That's what we're going to discuss next half of this third lecture. Before that, if you want to get a short break, we will get it there. Plus, if you have any questions, we can ask right now. Any questions or anything to be discussed? If not, I will end the session because I don't want to have a longer recordings. In the last week, I think you got the longer recordings. So I want to get shorter recordings so you can follow it later on. Because of that, I will end this session to make the recording possible, and please join back by 5 minutes time for the next half of this lecture. Let's take a 5 minutes break. for the moment and join back at 9:30. Let's say 9:30, we will join him back, right? So I will stop the session for 5 minutes.